kind of ambitiously, I decided to include an additional example in previous semesters. And why not include it this semester, although it's wicked long? So, but let's try it out anyway as part of this. So this is problem 14.1, and I made it more complicated by asking you to do the estimate the fatigue safety factor, or the life if it fails, right here. So a spur gear pinion has a pitch of 6 teeth per inch, 22 full depth teeth, and a 20-degree pressure angle. The pinion runs at 1200 RPM and transmits 15 horsepower, right? So we're doing the problem a little backwards, to a 60-tooth gear. If the face width is 2 inches, estimate the bending stress. Okay, so I almost want to like look this up and see what the power would be based on Boston gear, but be kind of an interesting thing to see. Boston gear catalog, and here's our 6 diametral pitch, 20 degrees. They do have a 2-inch is the face width, it turns out. They don't have 22 teeth, but they do have 21 teeth. The RPM is 1200. They don't quite go to 1200. You can see this like little line right here. I think that might be, they got some kind of indication somewhere about what that line means. But we could interpolate between 21 and 24 right here to see what they're saying. And so theirs has something, it would be somewhere like 25 or 26 horsepower is what they're saying the capacity is, versus their 15 horsepower right there. So we want to estimate the bending stress that's as part of this. It's it doesn't look like the thing, depending on what material you choose, would fail in terms of this range. But it's a good idea to, I think, to take a look there and make a comparison. So here, going through the motions here, one of the first things we're going to do is let's figure out what the pinion is going to be. And I'll write dp because it's the number of pinion teeth divided by the pitch. And let's see, let me arrange this here so it won't be square here, but it'll be more comfortable for me to write. And so this is going to be 22 teeth, and the pitch is 6. So we're going to have 3.667 inches diameter. So now let's get the pitch line velocity, pi dn over 12. So pi 3.667 are 1200 RPM divided by 12, and I get 1,152 feet per minute. They didn't tell us how the teeth were cut, right? They said spur key. So we're going to go ahead and assume again that it's going to be a the cut and, I think it's cut and milled. Is that the right terminology here? Let me double check right in there. We're going to come back and cut or milled profile right there. So we're going to use, that's the equation that we're going to use. And so we take the 1200, add the 1,152, and the 1200, and what we're left with is 1.960 is our dynamic factor. We also will look up in the book that we have right here. Let's look up what our Lewis form factor is going to be, and that is out of table. I think it's like right there at the beginning. It's like table 14.1. I think in that chapter. It's really early on. for stuff. 14.1, yeah, table 14.2. And we had, what did we say? We had 22 teeth. Is that where we have 22 teeth? So we have 0.331. This is 0.331. We're going to find out what our transmitted load is going to be. We know that. We can take 33,000 H over V, right? So 33,000. Our power, they said, was 15 horsepower. Our V, we found out, was 1,152. So we get 429.7 pounds. All right, so I think we have everything we need here to find out our stress. We're going to have a KV, WT, pitch, divided by our face width and our Y. So we have 1.960. We just found 429.7. Our diametral pitch is 6. And face width is 1.5 and 0.331. Something I want to point out here is a larger pitch will give us a higher stress. That's an interesting thing to keep in mind, and maybe something I should have pointed out right here when we did the derivation of the thing. So sometimes when making design decisions about the arrangement of something, we'll try to get the size to be something that's going to be useful to us. You know, we'll make it the diameter much smaller when we have a larger pitch, right? Which can really help us with our arrangement, but we increase the stress. So that is a design consideration we have to keep in mind. So what we end up with is 7,633 PSI. You're aware of that, right? So if we were to assume it's the 1020 hot rolled steel with a yield strength of 30 KSI, we would find out a safety factor. We would take now and have the yield strength divided by the stress, or 30 divided by 7.633. And we get a safety factor of 3.93. And remember, I don't want you using more than 2 decimal places in a safety factor, because we don't want to imply more certainty than we have. Now, if we wanted to do this for fatigue, right, and so this is where this becomes a long problem right here. We want to go through all the different steps that we had in the previous example in 14.2. So this requires us to have our own endurance, really, to be able to do this. So once again, if we looked up the ultimate, we would have, assuming once again that it's this right here, we know that our SC prime with the 0.5 times our 55 was 27.5, right, KSI. And then KA, we would have the identical KA that we had in the previous problem, which you recall I had to change because of the 11th edition. Now, if you're using the 9th or 10th or even the 8th edition right there, that's totally fine. I'm gonna switch back over to the numbers that I have instead of recalculating all of them to reduce the video length. But as part of that, remember that this is what we did to get this, and then we looked up these A and this B, and we used machined for right here. And so for mine, I got 0.9336, right? The 11th edition will give you different numbers. I believe the 11th edition gave us 0.8382, right? So it would have been a smaller number. We also are going to, because we have a different pitch right here, we're going to get a different tooth thickness, right? So we're going to have a different circular pitch, which is going to be pi over p, right? So that's going to be pi over 6 now compared to the previous problem. And that's 0.5 a 2, 3, 6. We decided that the tooth thickness was approximately the circular pitch divided by 2. That ends up being 0.2618. That means that we're going to have a different equivalent diameter for this thing, and we used 0.808 square root of ft for this right here. So putting this in here and also putting in the 2-inch right in there, we end up with an equivalent diameter of 0.5847. Remember that equivalent diameter, that would be the equivalent round stock that we would have compared to having a rectangular cross section. Is what they're saying. A rectangular non-rotating cross section. That's also part of the deal with the having the equivalent diameter here. And what we end up with this is we have, if we put it into KB right here, we get with that, remember that's the 0.879 diameter raised to the negative 0.107, right, for that range. We end up with 0.9310. And these aren't very big numbers right here, so they don't really change this SE all that much. So we have the SE, it's going to be, remember, KA, KB, KC, KD, KE, KF, and SE prime. We could treat, this one's going to be 1 because we are bending, right? So the loading is the apples to apples. The original laboratory test that you would get for a beam bending isn't bending, so that the load type is 1. We don't know anything about the temperature. We don't know anything about the reliability. It didn't tell us it had to be anything more. And this miscellaneous, we are always treating it as equal to 1, even though the example 14.2 does create a new miscellaneous factor that accounts for Goodman or Gerber, right? So this could be 1.33 for Goodman, could be 1.66 for Gerber. It is material dependent, I believe, so we have to be aware of that. So, but that would be like sort of the range of what that would happen right in here. It is a simpler way to approach this thing. But anyway, if we put all these numbers in here, this number, and this number, and then 1s for all of these other things, we get 23.9 KSI, and I should have 4 sig figs right in there. Once again, something that's interesting that happens when you make this assumption right here, that you say that the radius of the fillet radius when trying to get the stress concentration right here. So if we put this rec in here with that 0.3/6, right, and this is not written anywhere but in the example, but this is an estimate of the fillet radius is based on this 0.3 over the pitch. You end up getting 0.0500, whatever. And then if we want to have that radius over the diameter, or the radius, not diameter, radius over that thickness, that's going to be the same thing as the radius over our tooth thickness for us, right, for a stress concentration, and we get 0.191, right? And if you put those two in there, interestingly enough, you get a stress concentration of about 1.5, which is about the same thing that we found in the last time we did it. Interesting. I think so. Okay, and then if we go and find Q, we estimate Q based on the material right here, once again, and we also, based on this radius right here, we get 0.655. So if we want to find our fatigue stress concentration, we take 1 plus Q times KT minus 1. So it's 1.5 in there, 0.655 in there. We end up finding 1.33 is our stress concentration, right? And so what we would then do, right? Because we're doing it in this direction as opposed to in the previous example where we were trying to find what the horsepower limit was. We were given the horsepower. Let's try to find the Goodman safety factor here. So our stress, what we're going to say, is going to be KF times the nominal stress, right? So this is the nominal stress is what we're going to say this guy was, right? That's without stress concentration. So now we do have stress concentration, fatigue stress concentration. So we have 1.33. We're going to multiply it by our 7.633, and we end up with 10.13 KSI. We know that our alternating and our mid-range are both going to be equal to the stress divided by 2, right? 10.13 divided by 2. And you're going to ask, why do we know that? Because you know that this is max minus min divided by 2, and this is max plus min divided by 2. Min is both 0 on both of them, so it's just the max divided by 2 and the max divided by 2. Both of them are same. This is the maximum stress divided by 2. All right, so hopefully you will buy that. And I got 5.066. So if we want a Goodman safety factor, 1 over sigma A divided by SE plus sigma M divided by SUT, right? We plug all those in there and we get a 3.29. Remember, that's the safety factor for infinite life, right? So if you want infinite life and you want to be assured of it, here's how much assurance that you have, right? This is to account for the uncertainties that you have. So hopefully that it's a 17-minute video, shorter than the other one, but the other one I definitely went into much more detail into how you got through some of these other factors right here. So you're going to be expected to be able to understand this type of thing and asked to do problems in an exam or in homework where you would apply the Lewis equations. So the next class is going to be class 8, and we're going to recover some of this because we're going to do at least one example where we go all the way through, where we cover and evaluate for both bending fatigue, which is this one, and also for contact. So thank you.